Okay, so now let us solve this problem, and please pay attention because this is a very important problem for the understanding. So basically, let me just remind you the general procedure, like I always do. So step 0, read the problem, do the input-output. Step 1, do a figure that will be used in order to write down the main equation to solve the problem. If at this step you have enough information to solve the problem, you can just go to step 4 to solve it. If you need additional equation, you go to step 3. Okay? So let's read the problem. 1 kilogram of oxygen is heated from 20 to 120 degrees Celsius. Determine the amount of heat required when done in a constant volume process, and B, an isobaric process. Okay, so basically constant volume process will mean this. So V constant. And an isobaric process means constant pressure, and that only happens when you have a piston cylinder and this is free to move up and down. So in each one we have M equal 1 kilogram of oxygen and is heated 20 degrees Celsius to 120 degrees Celsius, and basically what we are asked to find is what is the amount of heat required to do that. Okay, so what is this problem extremely important is that you will find out that the amount of heat to heat up the 1 kilogram of substance of oxygen here will be different than here, and we will see that actually the amount of heat over here will be lower and here will be higher. Why? It's because here, in addition to heat up the volume, you also need to move the piston up. Okay, and in this case that doesn't happen. So you will see what happened with the constant of specific heat, and then I will do the problem in a different way. So let's say this was step 0. Step 1 probably is going to be very similar. Alright, just in this step I'm going to give a bit more information so that we see this is a closed system. I show the closed system over here, and the mass is unchanged, and we need to find what is the amount of heat that I need to put into the system, and this is case A, case B. Alright, step 2. So you know, for the first principle of thermodynamics we have 2 sign convention. Let's use this one over here. Q minus work equals to change in energy, and under this definition the work is equal to P dV. Okay, so let's just first solve the problem using the specific heats. So if you look at the figures over here, is there any work done? You cannot see really any W show anywhere. So this is 0, and for case A, what will you have? Q equal to M, B constant, so we have C sub V for specific heat at constant volume, delta T, this will be equal to M CV T2 minus T1. Okay? And CV T2 minus T1. So where do we find CV? CV, you need to get it from the tables. So it will be table A2. I don't know if you can read, but it's the top one, and you have the value for CV will be 0.718. So table A2 for, oh, that was for air, and we're dealing with oxygen. You see, you need to be careful over here. So for oxygen, it's down here. O2 is actually CV will be 65.8. Oxygen 65.8, but 0.658. 1, 2, 3. Okay. All right. And if we do case B, what do we have? Q will be equal. We have the same equation here, but this will be equal to M C sub P delta T. So that at the end we'll have Q equal to M C sub P T2 minus T1, where C sub P again will come from table A2, not table A2E. For oxygen is equal to 0.918, and the units kilojoules per kilogram Kelvin, kilojoules per kilogram Kelvin. Okay, so we don't need any additional equation. So step 3, not needed. And we can go to step 4, which is to go and solve. So for case A, we have Q equal M CV T2 minus T1. So this is equal to 1 times 0.658 times 120 minus 20. So this will give us that the amount of heat you need to put in will be equal to 65.8 kilojoules. Okay, and in case B, we have Q equal to M Cp T2 minus T1. So this will give us 1 times 0.918, 120 minus 20, which will give us Q equal to 91.8 kilojoules. Okay, so now let us go to something that is very important for the understanding. All right, so Okay, so basically what we did this case over here, V constant for this control volume, we had that Q basically would just be equal to the work on internal energy equal to M CV delta T. Okay, then for the second case, which is this one over here, constant pressure, I did it basically using the definition of the specific heat, but I want you to realize something over here. Really, this problem, we could break it down into work done to move, let's say, this volume over here, like if this was a fixed volume, forget about this top part over here, okay, plus the work needed in order to move the piston up in order to keep the pressure constant. Okay, so I don't know if that makes sense. But if we go back to the, for this case over here, this one here, if we go to the initial equation, the first principle of thermodynamics, this is what we have. Alright, so in this case over here, what do we have? Q will be equal to the internal energy plus now the work done by the piston. And we know that the work done by the piston is equal to P dV. Okay, there is the integral form, but here is not integrated yet. Okay, so this, in this equation, this will just be equal to P dV before the integral. So basically, this will be the energy needed to heat up an equivalent volume, and this will be the work needed in order to keep the pressure constant. The head of the piston will have to move up. So this equation here will become what? M CV delta T, like the one before, plus P dV. Okay, so this will be equal to M CV delta T plus work done at constant pressure, so P is constant, plus P V2 minus V1. Okay, so I'm going to go to the next page because we have some algebra. So let me just rewrite the equation. Q equal to M CV delta T plus P V2 minus V1. We can rewrite this as M CV T2 minus T1 plus P constant, and then we are dealing with oxygen. So oxygen is an ideal gas. So if it's an ideal gas, what do we know? PV equal nRT, which will mean that the volume equal to N R bar T over P. So V2 will become what? N R T2 over P2, but it's constant, minus N R bar T1 over P. And you can see right away what's going to happen. This is, the P will cancel out, and we will end up with M CV T2 minus T1 plus n r bar T2 minus T1, which is equal to what? M CV T2 minus T1 plus N is the number of moles, and you know it's equal to the mass divided by the molar mass. R bar T2 minus T1. So if I factor out the M T2 minus T1, we get here CV plus M over capital M R. Okay, and finally, I just rewrite this on the form M. Then that constant value over here, CV plus M mass over molar mass, gas constant, R times T2 minus T1. And if we compare this equation here, okay, to this equation here that we had initially for case B, you could say that the CV plus M over M would be the CP. So let's go and check. Let's see if that's really the case. So remember, we had CP equal to 0.918. We might not get exactly the same thing, but probably will be close. So if we come now here, we'll have what? CP is equal to CV, which is equal to 0.658, plus the mass in this case is 1, divided by the molar mass of the air, of the oxygen. So what is the molar mass of the oxygen? You get it from table A1 if you don't know it, but basically would be 31.999, let's just say 32. 1 divided by 30, so 0. Divided by 32 times R, which is 8.314, but you should get that one from the conversion factors over oops, where is it? Over here. So it would be times 8.314. Okay, and if we do the calculation, we get the 0.9178. And what is the value we had from the table? I think it was 0.918, if I remember properly. Yeah, it's over here. Okay guys, so what's important over here is to realize what is that the CV, so let me do a figure. When you have constant volume, the change in internal energy would be proportional to mCV delta T. If you have a constant pressure, all right, the change in energy in this case could be equal to mCP delta T yeah, but really should be equal to change in internal energy plus the work done by the pressure. And probably on the next video, this actually has a name. But what's important here is that you remember that internal energy is related to the CV constant, okay? Cp delta T. And for this, we'll see what happens next time. Sorry for that if you not see it. So basically I was saying that what's important is that for constant volume, you remember that you only deal with internal energy, and internal energy will be equivalent or proportional to the CV delta T. When you have this type of system, for now, just remember that you have to deal with the variable Cp delta T, okay? Because this variable over here has actually one name that I will introduce on the next video. But if you want, I can give you the heads up now. This is what is known as the enthalpy. All right, thank you for your attention.